Right. Simple harmonic motion. You got that written down? Yeah. Continue. Yeah, continue. Yeah. So, sleepy? Okay. Now, the motion that we see when springs move is a special type of motion in physics. It's not just springs, but that's just one example. This is an example of what's called simple harmonic motion. So it's motion that basically is up and down, or left and right, left and right. This is simple harmonic motion, roughly speaking. And just like with circular motion, there's a special type of force that causes this motion. So I wonder if anybody knows, with circular motion, it was a force that was perpendicular to the velocity and towards the center of the circular motion. Does anybody know what type of force makes a simple harmonic motion, this sort of up-down force movement? Has anyone seen this before? You have, Marwan?
I can't
Anyone else? No? 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 It's gone?
Yeah.
Or you've never seen it?
You saw it.
It's gone. Okay. Right. So, if an object is undergoing simple harmonic motion, that's because there's a force which is proportional to its displacement and in the opposite direction. Now, before you write that down, I just need to explain a word here. Do you all know proportional? Yes? You know it? Okay, you're going to explain it to me. So, what's proportional mean? A proportional to B.
Because F equal NA, F is A is proportional to F. No?
Okay, you're giving it to me as an equation. So, like A equals KB, is it?
Yeah.
Yeah, okay, fine. In words, though, it means that if I double A, then B doubles. Or if I double B, then A doubles. That's proportional, okay? So what's happening here is the force is proportional to the displacement. So actually this is handy. If I have a bigger displacement, I have more force. So here, look, 0 displacement. 1 centimeter, 2 centimeters. The difference between 2 centimeters and 1 centimeter is the forces twice. And if I do 3 centimeters, 3 times the force. No, sorry. Yeah, 3 times compared to 1 centimeter. Okay. Also, the direction is opposite. So if I look here, if I move this to the window, which way is the force in the band? Which way is the force? Is it also to the window? No, there's a force backwards. Yeah? So if I release, you see it goes back. Okay. Now, the example with the spring, what would happen is you release it and it goes back, and then it goes this way, and then it goes this way, and then it goes this way. I can't do that with this. Okay. But you get the idea. Okay. Now, you'll need to write that. Well, I don't need it drawn because I showed you with my bicycle band. So you need to write that definition down. Do you think this definition you've seen before, Rahman?
Yeah.
Yeah. Marwan?
Yeah.
Okay, dokie. Continue.
Yeah.
All right. So, next now. Imagine a spring pulled out and then released. The velocity time graph of this typical motion is shown below. So you have a spring, you pull it and you release. What happens? So if I pull the spring up and release, what will it do first? It'll go down. So can you see that's why the velocity is negative at the start. It'll go down and then what will happen? It stops and then it goes back up. Okay? So on the diagram, where does it stop? That's here at this time. What's happening here? At its maximum speed. Yeah, so what happens is as it falls, it'll start getting faster and faster and faster and faster. And then it's going fastest. Then what will happen? It will slow down and then stop. That's this point here. And then what happens after it stops? Goes back up to maximum speed again, and so on like this, okay? So this graph here is the velocity time graph. They sometimes ask you to draw this in the exam. A typical question would be, they give you a spring, they say the spring is pulled and released, and they would say something like, draw the velocity time graph for 2 cycles. So tell me when I would need to stop for 2 cycles. So here? Yes, no? No. Here?
No.
No. Here?
No.
Here?
Yes.
Are we sure?
Yes.
I don't know about that.
No, it's supposed to be before 10.
Yeah, no, here, sorry, yeah, it is here. Yeah. Because this is, let's think about the spring. Down, whoa. Okay. Spring's going down, then spring's going up, and it stops. And then it's going up, and then it starts to slow down, it's slowing down, and then it stops. Oh, this is really hard to draw. Hang on, let me show you with my hand. Okay, now let's try and do this. Spring starts here, and then fastest, slowing down, stop, then up, slowing, and faster, slowing down, and hang on, I'm getting confused. Stop. I think I'm here now, haven't I? Yeah, okay. And that was 1 cycle, down and up. And you do it twice. Or if you look at the graph, down, up, down, that's 1 cycle. 1 period. And then there's another period. So here, didn't we say? Yeah. So what's that? That's about roughly 12 seconds or so in this picture here. So I'd like you to draw this for 2 cycles, 2 periods. Got that? Got that? Continue? Yeah. So, in simple harmonic motion, we have 3 terms which are also used in circular motion. So they are F, T, and omega. Now the meaning is kind of the same. So, you remember what F means for circular motion? Frequency. So what was F equal 2 hertz? What does that mean? 2 cycles per second. And for simple harmonic motion, same meaning. 2 cycles in 1 second. Okay? The T, periodic time. For circular motion, it's the time to do this. 1. And for simple harmonic motion, it'd be the time to do this. Okay? Fair enough. The omega for circular motion is radians per second. Okay? You remember, like 1 radian per second. Like a clock. But the omega, what the heck does it mean for simple harmonic motion? Are there any angles? Oh, look at the size of that seagull. Are there any angles? No. No, so what could it mean for simple harmonic motion? Yeah, but like describe it to me visually. What could the omega mean for simple harmonic motion? Yeah, but the unit's still radians per second. What angle? You know what I'm saying? Like, what the heck's the angle? If I said, oh, this has simple harmonic motion of omega equals 1 radian per second. Well, we know what it means for a circle, don't we? 1 radian in 1 second. Click, 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 so on. What does it mean for simple harmonic motion, though? That's not as clear, is it? Anyone think they know? Yeah?
When you draw a graph, it's like insane.
Nice try. Nice try, yeah. Okay, so look. The omega is still a type of speed, but it does not quite mean the same thing, since there's no angles. So what does the omega mean? Well, I have a picture here, and I'll draw another picture to help. We're all happy that this is simple harmonic, or circular motion, right? So let's imagine this is moving 1 radian per second. It'll go 1, 1, 1, you know, and so on. Okay. Do you see these things here? This thing here? It's moving left and right, isn't it? What type of motion is this? Simple harmonic motion. The omega here in the simple harmonic motion is the same as the omega here. In other words, if you connect the simple harmonic motion to a circular motion, the omega is going to be the omega you get when it's connected to the circle. The example my teacher gave me in high school, which I liked, and maybe you'll like it too. You imagine you have a wall here, and on the wall you have an old-fashioned record player spinning slowly, and you put on the record player a candle. It's got a little flame here, and the candle, you can see the little flame on the wall there. Okay, what way will this little flame on the wall move? Will it go left, right, up, down? What will happen?
Right.
Yeah, it'll go right here first, and then left, and then right. It'll keep going back and forth like this, won't it? Yeah? What motion is this? This is simple harmonic motion. And the omega here will be the same as the omega here. So there is no angles in simple harmonic motion, but if you connect it to a circle, then the meaning of the omega will be the omega for the circle that's connected. Yeah? Can you get the connection idea here? Yeah? Have you seen this before? This is something new maybe? Yeah? So I don't know which you prefer, the train or the candle, which is clearer example. Yeah, most people prefer the candle example here. So the omega does have the same meaning as an angle. Okay. Now, there's an animation that if you want to look at it later, that kind of helps you visualize this. Anyways, these are terms that are in common, so I think you should at least write down Ft omega as also terms. So you can write simple harmonic motion terms, Ft omega, and then you could write are the same. So you could say Ft omega are also in simple harmonic motion. You got that? Yeah? Okay. Now, here's some terms. Equilibrium, also called the origin. What's the meaning of that term? That's the center of the motion. So if you look at the example with the spring, it's going up and down, up and down, up and down like this. The equilibrium would be somewhere like here, the center of the motion. The amplitude. What's the amplitude? Does anyone know this word? I think someone might know this word.
The distance between the equilibrium and the peak.
Correct, yeah, yeah. The distance between the maximum and the center. Correct. In other words, the maximum displacement from equilibrium, as you say. Velocity, you know what velocity is. It's the same as what it always was. Angular frequency, also called angular speed. It's the same as the circle. Frequency f, the same as the circle. Periodic time, same as the circle. In fact, what's the only one that's new?
Amplitude.
The amplitude. Yeah. So I think if you want to add the top two here, the top two, write them down at least.
Slowly.
Snowing.
Oh,
Snowing, yeah.
Wow.
Yeah. Nice.
That's good.
It's good?
Yes, because I never see snow.
I've never seen snow before.
So in China,
Same.
the place we stay in Guangdong is like never snow.
Ah.
Always hot. Always
Yeah,
hot.
Nigeria is always hot.
Very,
Very hot.
You want to have class outside?
No,
No, it's okay.
After finish.
Okay.
I can't feel my
It's nice to see, but not nice to feel.
No. It's not too bad. It's not too bad. My heating system at home, you can see how many hours it's been on each week. So when it's a week like this, when it's snowing, every week it's like 20 hours, 20, 20, and then a week like this it goes 40 hours, it shoots up and then it goes back down. There's actually really big snowflakes blowing down. Can you see? Yeah.
Jason!
Alright, we'll close one of the windows now at least. Alright, you got that? Yeah? Okay. Now, next. You got that?
Yeah.
So, when the mass is at its maximum displacement, it's at rest. So it has no kinetic energy, right? It has only potential. As it starts to move, its potential energy gets converted into kinetic energy. When it's at its origin, it has no potential energy, it has only kinetic energy. That is when it's traveling its fastest. So anyways, below is a graph to help explain this, and this is also a graph they ask you to draw. Now before you draw it, I just want to explain it. So here is the displacement, and here is the energy. So if you pull the spring out all the way, okay, what kinetic energy will it have? 0. Okay, and then you let go and it starts to move. What happens to its kinetic energy? Increase. So as the displacement gets smaller, the kinetic energy gets bigger. And then when is it biggest? At the center. And then what happens? It starts to slow down and then stops. So you see the kinetic energy goes up and then down here. The potential energy must be the opposite. Why? What rule in physics tells us the potential energy must be the opposite? Conservation of energy. When we have no kinetic energy, we must have potential energy. Yeah, and then vice versa. When we have no potential, we have a lot of kinetic. So the potential energy does the opposite. It goes from high to 0 to high again. If you add the potential and the kinetic together, you get this line here, which is total energy. Why is this line a constant flat line? Yeah? Give me a full sentence.
Just like the candle.
Come on, you have it. Just give me a sentence with a verb, you know?
Like potential energy and kinetic energy.
Yeah, come on.
equal
Alright.
the total.
Yeah?
Net force.
Yeah? The total energy is a constant. It doesn't change. The kinetic plus the potential at the beginning, the end, or the middle, always the same. Okay. So this is a graph they sometimes ask you to draw. I just to be clear, kinetic, potential, total energy.
Displacement.
Yeah. Oh, Jason, we better close that window. These students are looking cold. Cold. Cold?
Not cold.
No? Well, he's cold.
Jeffrey.
Cold?
Yeah.
Yeah.
Sensitive.
Maybe he comes from a hot part of China. You come from a hot town in China?
Not like us.
No. This place is cold.
Is it? Is it really? Your hometown? Hot or cold?
No.
Jeffrey.
No. Cold?
How far is cold? Big snow.
Really?
Yeah.
Really? Okay.
I
Jeffrey.
have read in his hometown.
And it snows?
Yeah.
Oh, okay. So this is like home. Right, have you got that drawn? Did you draw that? Can you see all the words okay? Kinetic, potential, total. Jeffrey, I'll help you. Kinetic, potential, total. Chilly, huh? I'm glad I had that breakfast burger. It's starting to turn into rain now. No snowman.
This is the snow is late.
Sleet.
Late.
Late? Yeah, I guess a little bit. But it's still kind of, what date is the date? 11th of February. No, it's still okay. This might be the last chance though. It's like this should really be the last cold weather front, I think. Things will start to improve now over the next few weeks. Yeah. It can be a little bit strange in Ireland. You know, March can sometimes be very cold and sometimes very hot. It's like 50-50.
How
Yeah.
hot?
It can get very hot. Like, I remember one March, you know, there was snow, and then one March, you know, the weather was like 21, 22
That's
Celsius.
That's
Yeah. That's, right now, what is it, like, what is it now, 6 or something?
You have to divide it.
This one is
like
2.
50.
2.
Yeah.
Yeah.
You have to divide
So
50.
trust me, 22 will feel quite nice after it being 2. Yeah. Right, okay, have we drawn that? Yeah. Alright, so,
Technically, it's cool in my city.
is it? Well, it's hot here. Okay, now, I don't need you to draw these, but I just want to give you the idea. If you were to look at displacement, velocity, or acceleration, you notice something very similar to the graphs, don't you? They kind of have this increase, decrease situation going on. And we'll see the reason when we look at the formulas. And now we're going to have a look at the formulas. Now, some of the formulas are the same. We did this formula for circle, didn't we? That's the same. This one, the same. This one, this one's the same. Yeah, it is. Oh, it is. Now, this one's new.
Minus.
Yeah. The minus is because of the opposite. When it's moving to the right, the force is to the left. And S is displacement, or sometimes X, whatever letter you want to use. Now this one, I have to explain it before you write it down. This is, I see, look at this, Stephen. I started using S and then I switched to using X.
Let's maintain.
Which would you prefer?
X, because S is for S. So X.
The class has spoken. They want S. Whatever you prefer. Okay. Whatever you prefer. Now, before we continue, there's two types of simple harmonic motion. You can have motion which starts at the amplitude and goes like this. So look, it starts here and goes like that. Okay, starting here. Or you can have it start in the center and goes like this. Okay. If it starts from the center, the equilibrium, then you use sine. But if it starts over here, then you use cos. Okay? Most of the time, where do you think it will start in the exam questions? Now,
Hi. How are you?
son, where's Dammy? Dammy. Okay, come on.
Sorry. Oh, damn you. How for you?
So what happened to you?
My lip card finished when I was about to enter the second boss.
And you had no cash?
No, like, so I had to like go and like buy it. So like,
Okay.
I have to go snap.
So what have you learned?
Always check your.
Yeah, always check your leaf card, yeah, okay.
You know my case?
Hmm?
You know my case?
Yeah, I got your email.
Oh yeah.
No, no.
Look, he knows now, he's learnt his lesson.
Yeah.
Now, let me give you a tip to help you remember, okay?
What?
Come on, sit down, sit down, sit down, come on. I'm trying to-
Yeah.
Okay, so, let me give you a little tip here to remember which is sine and which is cos. Okay, so if you look, would you say this is on the outside or the inside? Outside. And if it starts here? Inside. And what's the middle letter of sine? I. And of cos? O. See where I'm? Yeah. Inside, outside. Yeah. Yeah, it works, right? Now, the next one is for V, and it's the opposite. So if you use sine here, then you use cos here. And if you use cos here, you use minus sine here. Now, why minus sine? Well, think about it. If I'm using cos, am I starting on the inside or the outside? The outside. The outside, the O, for outside. And the first thing it does is does it move further out or back to the center? Back to the center, and that's why the minus is there. It has a negative velocity. Yeah, because if you think about it, if it starts on the outside, will it start to move left or right? Well, it'll move left. Yeah, so that's why it has to be a minus. Okay. The next formula, the reason for the plus and the minus here is this formula can only tell you the speed, but it can't tell you the direction. Okay. So if you don't care about the direction, that's great. But if you do, you have to think carefully. Do I use plus or minus? Is it moving right or is it moving left? Okay. The next formula is the potential energy formula. So this is the formula for potential energy. Looking at this formula, what is the potential energy when S is 0? 0. Which, remember, we said has no potential energy at the center. Also, what type of graph will this give us? Yeah, go on, go on. What type of graph will this give us? What shape? If I put potential energy on the y-axis and S on the x-axis, what graph will this make? Quadratic. And isn't that the shape you drew a moment ago? Yeah. Right, so there are 7 formulas, and please change this one to an S here.
S is distance or displacement?
Displacement. Okay, have you got that?
Yeah.
Yeah? You got that? Okay. So, in the real world, this is what really happens, isn't it? The simple harmonic motion doesn't continue forever. Eventually it slows down and then stops. This is called damping. And they sometimes ask you to draw a graph demonstrating damping. What's causing this damping? Yeah, but what's the cause? Friction. Yeah, the drag. Yeah. Yeah. Okay? Got that drawn? Yep. Now, this one is interesting. This is called the forced harmonic oscillator. Now, I'll explain what's happening here. So, imagine you have a spring, and you have this little mass at the end of the spring, and it's moving left and right like this. Okay? Then what you do, at the end of the spring, you attach another harmonic oscillator here. So not only is this moving left and right, but at the end here, this big one is moving left and right. And we all understand that this guy, it will affect the motion of this guy. Right? So this is moving left and right, and this one's moving left and right. And my question is, how will this affect this? And what's interesting is the F, the omega, and the T, they don't actually change, which is very, very strange, you might think. So imagine that this has a frequency of 2 hertz. So in 1 second, what does it do? 2 cycles. Then I turn this on. So I turn it on and it starts to move. You might think its motion will affect the frequency here, but it doesn't. Also the omega and the T, they don't change as well. Now that's obvious, because what's the formula for T? It's 1 over F. And what's the formula for omega? 2 over T. So of course if the F doesn't change, then these don't change either. But I think that's interesting. You might think, oh, if this is going really fast, maybe that will make this one move really fast as well in frequency. It doesn't. So the question now next is, only the A changes. So this has a small amplitude. If this starts moving, it could make the amplitude here bigger. My question is, what movement would I need here to make this amplitude bigger? What are my choices? I could move this fast, I could move it slow, I could move this with a big amplitude. Any ideas? How should I move this to make this one's amplitude bigger? So you're going with a slow motion, okay? Any other ideas? Let's see what people think. A high frequency here. High frequency, okay? So we have a slow frequency and a high frequency. Any other options? You're going with slow frequency, okay? Any other ideas? You're going with a high frequency? Anyone else want to give an opinion? No? Look at you all thinking hard. Any other opinions?
And the same frequency as the smaller.
There you go. Rahman got it. So, high, wrong. Low, also wrong. The answer is, the frequency here, if it matches the frequency here, you'll get a bigger amplitude. And you can see this on a graph. So, I call this frequency here F0. Okay? If this guy has a frequency less than F0, you get less amplitude. If you have a frequency very high, which is what a couple of you suggested, you also get less amplitude. In fact, only when the frequency matches F0, a middle value, you get the most amplitude. Yeah? Oh, you look so unhappy with this, Ming. You look so unhappy. What's wrong?
No, I just new.
You knew this?
No, it's new.
Oh, it's new. Okay. Yeah, I think this maybe is new for people. Yeah, Marwan, you can accept this or you don't accept it. Now, I'm going to give you an example of where you see this in an area you already know. So you know, for example, maybe you know this in chemistry, this table is made of molecules. Are the molecules stationary?
Yes.
They're moving, aren't they? How are they moving? Yeah, but what type of motion? They're vibrating.
Yeah.
Now you can't see it, but all the molecules in this table, they're vibrating. Okay. So if I took a glass, are the molecules in the glass stationary? No. What are they doing? They're vibrating. Okay. If I put some energy into it, if my energy has the same frequency as the glass, then you can see the glass shaking. Why? Because this is happening. You are matching the frequency of the glass. So you're making the amplitude of the vibrations bigger. So big that you actually can see the molecules vibrating. And then it breaks. Okay? Another example you would have known before is the example with the bridge. The wind is blowing. If the wind blows at the same frequency of the bridge starts to vibrate with a greater amplitude. So it's not about having a high frequency, it's about matching the frequency of the object. That causes a greater amplitude. Yeah? Do you understand? Have you, like those examples I mentioned, you've seen them before, haven't you? Like breaking the glass. Yeah, or the bridge.
Yeah.
Like an opera singer.
Yeah.
The opera singer breaks the glass not because she's singing at a high frequency, but because she's singing at the same frequency as the glass. Yeah? What's wrong? Is it difficult to believe, or?
Well, they show it in movies now.
Yeah.
It's just that if I can break the glass with my voice,
No,
you
can't do
Not maybe not you.
Not you. It's only son that can do it, maybe.
Yeah.
Son.
No, what you need to have a skill. So what the opera singer does is flicks the glass and hears the frequency and can match it perfectly.
And somebody would tell me I can't fly. See,
what do they call that? Pitch perfect or something. These are people who can hear exactly the frequency, perfect pitch, isn't it? These are people who can hear the exact frequency of notes and match it. So this is the skill that you need. Okay. Now, I think it'd be great if you draw this and this.
I can't see the word on the left.
Piston,
No, but yeah, that's
amplitude. the example with the bridge, I can't remember the name of it, but there's a famous bridge in America in the 1920s, I think. You know this one? It collapsed during a storm.
Yeah.
Video.
There's the video of it, yeah. This is because the wind was at the frequency of the bridge.
Now go, bro. Physics.
Civil engineering problem. The engineer missed this physics class, it would seem.
Oh, this bridge?
Let's see. No, not this one. Here.
How strong was the one that collapsed it?
No, not that strong. It was just a frequency. Is this? Let's go to Google.
Okay.
Okay.
Which bridge do you like to use?
No, it's not.
It's not the beauty he's looking for.
I only know the London Bridge.
Son. But I thought, does it have to do with resonance or?
Tacoma Bridge.
Oh, the Tacoma Bridge.
1940s Tacoma Bridge.
I see.
That's the name of it. Okay, continue. That's amplitude and frequency. Okay, Hans. Okay, have you got that?
No.
Yeah. Absolutely.
No, Bello, I said you don't need to write this down. I just want the pictures. I mean, you can if you want to, but I need to move on. Because what I have to do now is examples, of course. There was another example more recently in the UK. I think it was the Millennium Bridge, and the Millennium Bridge, it used to swing quite a lot, and the reason it swung quite a lot is because the frequency of the bridge was the same frequency that people walked at, about 1 hertz. So as large groups of people walked across the bridge, that caused the amplitude to increase. Yeah. So if you want, you could look at YouTube later. Tacoma Bridge in the US or Millennium Bridge in London are 2 examples of this effect. Yeah. Okay, continue now. So, a boy pulls at a spring 5 centimeters and releases. The spring begins to vibrate. It takes half a second for the spring to complete 1 oscillation. What is the value of omega? And hence how fast is the spring moving after 1 second? Okay, I think... Yeah, this is an easy one to get started. So I'll just give you a minute. Look at the formulas and use the formula that will give you omega, and then a formula that will give you V. Oh, is it starting inside or outside? Outside.
So starting from outside, if it is velocity, it's minus sign, right?
Correct. Although I don't care about the minus, Bello, because I just asked for the speed. So, yeah. Right, did you calculate the omega? I think the best formula to use is omega is 2 pi over t. So you get, what's that, about 12 seconds?
6.
12, yeah, okay. And what about the V?
Zero.
Correct, but you don't need to know the amplitude. It was a trick. The V is 0. Why is it 0? I'm trying to trick you here. Come on. Why is it 0, the V? You think you know?
I thought
Yeah, why?
it's because sine of 4 by.
No. That's not what I was thinking.
Yeah.
Yeah?
Because after one second, it's already like completed.
Yeah, after 1 second it's completed how many cycles?
Yeah.
2. How long does it take to complete 1 cycle?
0.5.
So, think about this. It starts at rest, doesn't it? After half a second, where is it?
At the top.
Back at rest at the top. After another half a second, where is it? Back at rest at the top. So 0. So I tricked you. I had you all thinking you had to do a calculation. Well, no calculation was necessary. Okay? Yeah. Okay. Next example now. Now this one is more like a calculation. A molecule is vibrating with a frequency of 1420 megahertz. By the way, this is like a realistic value. You know, it's not a made-up number. I think this is the frequency a H2O would vibrate at. I think H2O is vibrating at this frequency. I'm not sure though. The amplitude is obviously quite small because you can't see it vibrating. So it's 2.93 times 10 to the minus 15. Right, the first one is what's the omega? So you could say omega is 2 pi over t and t is 1 over f. So omega is 2 pi f. Okay, so let's calculate this. Did you get the omega part?
Yeah.
What's the omega, Marwan?
8,920.
Do you agree?
Yes.
Good, okay. Now the next one, before you do it, some idea perhaps how to do it. What is the maximum velocity? Now I'll go back to the formulas and maybe someone can give me an idea. Maximum velocity. Well, think about this. When will it be travelling at its maximum velocity? Where? At the centre. So that's when S is 0. So if S is 0, according to this formula, what is the maximum velocity? Omega A. If S is 0. Do I care about the minus? Well, really, I want maximum speed, so I don't really care. No, I don't care about the direction. Wait, before I continue, we have the second half. What about maximum acceleration? So again, I don't care about the minus, all right? But at what value of S will I have the maximum acceleration? Yeah, which is what? What's that called? Maximum displacement. Amplitude. So what is the formula for maximum acceleration? Omega squared A. And what's the formula for maximum speed? Omega A. Yeah? Okay. So give me the maximum speed and acceleration now for that molecule. The question? Yeah. Okay? You got that?
Sorry, the one for the acceleration. A is equals to minus omega A.
No, we said minus, well, we don't care about the minus.
Yeah.
Omega squared A.
So A. Okay, the big A.
Big A, yeah. Right, what's the maximum velocity here? What did you get?
2.614 times 10 to the power minus 11.
Did you all get that?
Yeah.
Meters per second. And maximum, yeah?
Don't you have to change the unit to hertz?
Yeah, because like that is good.
For which part?
For the first one.
Did you change this to hertz?
Yeah, it's
Yeah.
1.4 times 10 to the power minus 9. 10 to the power 9.
10 to the 9, yeah. Did you not do that? Ah. Alright, well let's try this again then. What's the maximum velocity?
8.92 times 10 to the 9.
Okay. Yeah?
Oh, that's the. This is for your.
Yeah, I don't get that. Sorry, that's the
He
angular.
told you the angular.
Oh, okay. What's the maximum velocity?
2.61 times 10 to the negative 5.
Did you get that? Main, what did you get for maximum velocity? Okay, Aoife? What'd you get for maximum velocity? Oh, come on. Kayhan, what'd you get for maximum velocity? Okay. Marwan, come on, guys.
But then how did you get 5? Minus power 15.
Look, V max
Minus
equals, we said, omega A,
Yeah.
which equals 2 pi FA, isn't it?
Yeah.
Yeah, so, come on, what is it? Marwan's going to tell me.
2.614 times 10 to the power minus
What is it,
5.
Bello?
2.614 times 10 to the power minus 5.
Okay, which is what you got, Rahman. Okay,
Yeah.
let's try this one. Maximum acceleration, what does that equal? What do we say? Omega squared A. Okay? Which is 4 pi squared F squared A. And Aoife's going to tell me this one. What's this one?
I forget the A.
You forgot what?
The angle.
You forgot it. Why'd you forget it? You need it.
The number.
Huh? Oh, the number. 2.93 times 10 to the minus 15.
Numbers are too big.
All right. So what is it here, Eva?
2.3.
Yeah.
Times 10 to the power of negative 19. Right?
Should be pretty small, I guess, because the F squared. Is this? Did you get this? Marwan? Marwan, did you get this value?
Yeah,
Oh.
the power matrix.
You're not sure about the power? Rahman?
Totally different.
Totally different, my goodness.
0.2,
0.2 is very different to 2.3. Come on, guys, you're just putting numbers in on a calculator.
Big numbers.
The calculator doesn't care. Jason, what's the answer here?
0.23.
No powers. 0.23 meters per second squared. Yeah? Really? Yeah? Maybe. Okay. I maybe could believe that. I want at least one other person to confirm this. Abdul Ali, what did you get for the acceleration?
2.23 times 10
Very big number.
Guys, what's wrong with you? Can't you just put numbers in on a calculator? Let me do it.
Is it like omega is like 6 times 10 to the 6, right?
I don't know what omega is, but you can use this formula.
No, I'm
Yeah,
talking
it's
about
better.
converting mega into
Mega.
six.
Mega is 10 to the 6.
Yeah, yeah. You converted it wrong.
Okay.
That's why I should be correct.
Yes.
Did you get this, son?
Yes, of
What
course.
did you get?
2.8.
It's 2.3.
23304.
I didn't even try.
2 point
I got tired of
2 by 3, 3 plus 10.
To the fifth.
10 to the.
fifth.
Yeah.
5.
Right.
Yeah,
Yeah.
Alright.
Yeah.
Oh.
Right,
It's
10.
10. It's 5 times.
Yeah. Yeah?
Two.
Huh?
That's right. I
Square.
calculated wrong.
Hang on, I can't hear you. Speak up.
Percentage square.
Oh, yeah. Thank you. Alright, continuing now. A car shock absorber supports a mass of 2,000 kilograms, is struck and begins to vibrate so that it oscillates twice per second and compresses up to 1 centimeter from equilibrium. How much energy is stored in the shock absorber when it's fully compressed? So you all maybe know this about cars. Under the car you have these big springs. They're called shock absorbers, right?
Yeah.
And when the car hits a bump on the road, the spring compresses and then slowly vibrates. But because of damping, it very quickly stops. Okay. So in this question here, what is happening is you have a car, it's coming along and it hits a bump. And it hits the bump and the spring compresses. How much does it compress? 1 centimeter. So my question is, how much energy is stored when it compresses? So what type of energy is that? Potential energy. And what's the formula for potential? A half omega squared S squared. So we know the M, right? Can we know the omega? Yeah. And we know the S. So give me the energy stored, please. Not quite yet for you.
Yeah.
Right, have you got an answer here? Let's have a look. So look, a half, whoops, M omega,
2000.
and what's the omega?
4 pi.
The omega is 2 pi over T. And what's the T? 1 over
So
F.
4 pi.
Yeah, which will be 4 pi then. A half M omega squared displacement squared, isn't it?
Yeah.
That's what I got. About 1 joule.
Sorry, what's the distance?
Hmm?
What's the distance?
1 centimeter.
So then distance are the same.
Okay? Yeah? Continue? You all have that answer? Just the formula calculation, yeah? Guys, what's wrong? Do you have this? Marwan, what's wrong?
I don't like 15, but
Also, we are good.
What way did you type it in? A half, right? Yeah?
2000.
M, yeah?
yeah.
Omega squared. 2 pi over T, and T is 1 over F.
No, no, wait,
Yeah.
wait, wait.
4 pi.
4 pi
That's
squared,
yeah.
and then 0.01 squared.
15 pi.
Well, how come my calculator is saying this
Can I
then?
see the question?
15
No,
points.
0.9.
The hertz is
Ah!
You wrote 0.5.
Ah. Well, that's going to change it to 15 though?
Yeah.
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 Because
Check and see,
4,
check
4
and see.
5 square.
Check and
Oh, look at that. I guess you're not all idiots when it comes to using your calculator. It's just for the last question. It just took a while to fully power up. Right, okay. Thank you. Okay.
Sorry, please, amplitude and displacement.
Yeah.
They are the same.
Yeah. In this question, they are. Right. Did you write that one down? Yep. 15 joules of energy is stored in the spring. Right. So, we've got 10 minutes left, which is good. Let's see. I think that's going to be fine for you to practice some of these. Did you get all of the circle questions finished?
No.
No. Okay. How many simple harmonic ones are there?
3 or 4.
Only?
That's enough.
God,
Yeah, 3.
this guy.
All right. So, what your homework is, which you can start now, is those 3 questions plus the questions you didn't finish last night. Yeah? Okay, so get started.
My physics knows, see what is left.
Yeah, aren't you lucky? All that physics you're learning.
Or piling up.
Piling up.